So now I want to convince you that Newton's second law is an example of a differential equation. So here's an example of a system whose state can be represented by one number, the position of a particle in one dimension. So here we will let x be the position of a particle in one dimension. The particle doesn't actually have to live in a one-dimensional world. Maybe it's just moving along one dimension or moving along some line, linear trajectory, and all you're interested in is how far along the trajectory it has gone. So maybe the particle is a simplified version of you making a road trip from one place to another, and the one dimension is the path that you're traveling along. Actually, since I'm going to talk about Newton's second law, let's say that the one-dimensional trajectory is actually a one-dimensional world. So here you've got a particle, and let's say it's restricted to this line, and x is the position, and it has to be measured off of something, so there's some origin somewhere, right? And the best situation would be one where we know what is x of t. If we know x of t, then we know the motion of the particle, right? At any given time, I can tell you where the particle is. Okay, but if we don't know x of t, then what do we know? Well, it depends. I haven't really said much about this world here, but often we can describe physical effects on particles in terms of forces. So let's say we know about some forces. So let's say F is the total force on the particle. Then Newton's second law says F equals ma. Let's suppose that m is the mass of the particle. So m is just a constant here, and a is the acceleration, which means what? It's the rate of change of the velocity, which is the rate of change of the position, which is what we are called x of t here. So the acceleration is the second derivative of x. Now, the force, I didn't really say what the force is, because that depends on the particular setup you have. If, I don't know, maybe it's gravity or electric force or something. Let's just pretend that, or assume that the force is something that possibly depends on where the particle is, and maybe it has explicit dependence on time also. So the force is going to be some function of position and time. Then here's the equation that we have. Some function of x and t, so something involving x and t, equals m x prime prime t. This is an equation that involves an unknown function, x, and its derivatives. And so this is a differential equation. So you can see why knowing how to solve differential equations would be an important skill. Newton's second law is used all over the place, right? That's a differential equation. So that's just one example. Here, the highest number of derivatives that shows up is 2. That makes this a second-order differential equation. So the order of a differential equation is defined to be the highest number of derivatives that shows up in it. So for example, we just saw that Newton's second law is a second order because acceleration is 2 derivatives of x. If I write an equation like this, x prime equals 3x plus t, then this is a first order differential equation because at most there's one derivative showing up there. If I do this, then now suddenly it's a third order differential equation. So it should kind of remind you of degree for polynomials. The degree of a polynomial is the highest power of the indeterminate that shows up. The order of a differential equation is the highest number of derivatives that shows up. I personally think this is actually not so good of a definition because, I mean, if I add x prime 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 and then subtract that, then isn't this the same differential equation? I mean, is it? And wouldn't this seem to now suddenly have order 4? Okay, so maybe it's not a perfect definition, but you get the idea. We'll spend a big portion of the first week, or maybe more, on first-order differential equations and methods for solving the easy ones. Then we'll spend time on second-order differential equations. And actually, typically in practice, you don't see much higher order than that. A big part of the reason for that is that I think a big part of the reason for that is that Newton's second law is a second-order differential equation. And even though sometimes it doesn't look like you're using Newton's second law, in physical applications, it's there somewhere. So you might be using a different model, but somehow it is very likely influenced by Newton's second law somewhere, at least for physical models.